So we're now working on trying to show that the inverse function theorem applies to our function capital F. And in this video, we will show this portion of what we need for that. So we will show that capital F is C1. Now, for this, theorem 9.21 is going to be our friend. At least I think it's 9.21. Let me look that up. Right, it was 9.21. So that theorem tells us that a function is C1 if and only if its partials all exist and are continuous functions. So we will use theorem 9.21. We will try to show that the partials of capital F exist and are continuous functions. So by partials, what I mean is now we'd like to examine these. The partial derivative with respect to the jth variable of f sub I, the ith component of f. That's what the partials look like. That's what they are. So you've got one of these for each how to put this, for all ij in there. So in other words, you have an n plus m by n plus m matrix's worth of these partials to look at, and we'd like to verify that they are all continuous on to use the inverse function theorem, we just need them to be continuous on some neighborhood of x naught, y naught. But in fact, we're going to show they're continuous on E, and that they exist. So these derivatives exist and are continuous on all of E. So in order to talk about the partial derivative with respect to the jth variable of the ith component of f, we should figure out what is the ith component of f in the first place. So what exactly is f sub I? So that's going to be determined by the definition of f, which is up here. So for xy in Rn plus m, we have f of xy is going to be some n plus m tuple, right? So you could think of it as its first component, comma, its second component, etc., all the way up to its nth component. You might stop your list there at first, and then continue, n plus first component, and so on, up to the n plus m component. And of course, any vector you can split up and write up as its components. But what I want to do is just put down in some nice usable notation what is the ith component in general for any given index I. So this list is supposed to be this list. Okay, but this is a list of 2 items. But remember, we're thinking of a list of 2 items where the first item is an n tuple and the second item is an m tuple. We're thinking of that as a list of n plus m items, actually. So the first item would be the first component of f, the first component of f of xy, and so on. We keep getting these up through all n components of f. And that's all the components of little f. And then next we start listing the components of this. So you could call those y sub 1 up through y sub m. So another way to so I mean this is telling you exactly what are the components of capital F. And I'd like to state it this way also. So just copy this over, and then here, instead of just writing y sub 1 through y sub m, let me write it like this. This is what you get. So y sub 1 Okay, so what we're about to do is think about the partial derivatives of the component functions that I'm writing down. So I want to think about the component functions as functions on their own. So I want to think about the mapping xy goes to the ith component of f evaluated at xy. So one function whose partial derivative I will consider is xy goes to this. Another function is xy goes to the next one. Another function is xy goes to the next one, and so on. And some of the functions that I'll be considering are the mapping xy goes to y1, xy goes to y2, etc. Those functions are pretty standard functions. xy goes to y1. That's a projection. It's a projection map. So let me use pi for that. It's pi n plus 1 of xy. So when I say pi sub n plus 1, I mean the mapping that takes an n plus m tuple and selects out the n plus first component. So if you take this, which is an n plus m tuple, and select out the n plus first component, you get y sub 1. And so on, like this. So this is nice, because now I can state exactly what is f sub I. So when I is in the range 1 through n, f sub I is, capital F sub I is little f sub I. And when I is in the range n plus 1 to n plus m, we have capital F sub I is just pi sub I, where pi sub I is this projection map. So just to be clear about which kind of projection map I'm talking about a projection map from E to R M. I'm sorry, to R. It's a projection map to R, which sends any vector, let's call it V, where I'm thinking of V as an n plus m tuple, sends it to its ith component. Okay, so again, what I'd like to show is that d sub j, f sub I, so this partial derivative, exists and is continuous for all I and j. So I'm going to split into two cases. There's I, so clearly we get a case split, right? There's I in this range, you get one kind of behavior, and I in this range, you're looking at a different problem entirely. So let's look at the first range. So when I is in the range 1 through n, and j is anything. So nj is any integer 1 up to n plus m. So j represents which variable we are taking a partial derivative with respect to. We have dj fi is just dj little f I, because capital Fi is little fi. And so it exists because it's this, and this exists and is continuous. So where am I getting that? Where am I getting that this exists and it's continuous? Remember, we assumed f is C1, right? F is C1 on its entire domain. So that implies that the partials of f exist and are continuous. That's not the definition of C1, but it implies it, thanks to, I guess we're also using Theorem 9.21 for that. Theorem 9.21 is an if and only if. So this statement here is thanks to Theorem 9.21 and the fact that f is C1. Okay, so that's all for the situation where I is in this range and j is anything. Now, we also need to consider I in the range n plus 1 up to n plus m. So then what happens? Sorry. N plus 1 up to n plus n. And j is anything. We have the jth partial of f sub I is the jth partial of, and we have decided what is f sub I. It's this function that we call pi sub I, the ith projection map. And so does this exist, and is it continuous? Well, the jth partial of the ith component of a function is the ij entry of the matrix representing the function in the standard basis, of the matrix representing the derivative of the function in the standard basis. So yeah, that's what you get when you evaluate at a point. So yeah, sorry, let me evaluate at a point. So whatever I say, I'm going to say that for all x, y in Rn plus m. Sorry, in E. For all x, y in E. And what I'm saying about all x, y, and E is that this, which I'm still actually wondering, does this a derivative even exist, is this, which I'm about to argue does exist and is continuous. And this is let me write this down off screen and then explain it. It is the ij entry of the matrix representing pi prime at xy in the standard basis. So what do I mean by pi prime? So that's not such a good notation to describe what I'm doing, but I just want to show you where it's coming from. So where am I getting this? I'm getting this from Theorem 9.17. Theorem 9.17 tells us what the components of the derivative of the matrix representing the derivative of a function are. So Theorem 9.17 says if you have a differentiable function, differentiable at a point, then the derivative at that point can be represented by a matrix in the standard basis, and Theorem 9.17 then tells you exactly what are the components of that matrix. They are partial derivatives. So Theorem 9.7 says that these partial derivatives end up being the components of a matrix representing the derivative of a certain function. What function? So I've called it pi here, but that's a bad name. It's the function whose ith component is pi I. So it's the function you get if you put together all the projection maps pi sub I into one big function. And what function is that actually? If you take all of these functions pi sub I and you make them the components of one big function, e to Rn plus m, running over all I, so make these all the components of a function of this type, what would that function be? So maybe guess, see if you can figure it out. Okay, and now I'll tell you the answer. That should be the identity function. So the projection maps are the components of the identity function. So it'd be the identity function on E. So let me go in and call it what it is. It would be the identity function. On the set E. So I'm actually doing a little bit more than I need to here for just what I said I would do. I said I would just show that capital F is a C1 function. And so to show that these partials exist and are continuous, maybe it's enough to just point out that since they are partials of pi I is a linear map, and linear maps are always C1. So that might have been sufficient. But I actually want to get a little bit more juice out of the work that we're doing here, and not just point out that capital F is C1, but also have a look at what the derivative looks like. So here we are getting the result that so first of all, the identity function on E, so yeah, we're concerned with two things: existence of this derivative and its continuity as a function of x and y. So definitely it exists thanks to theorem 9.17. The identity function is differentiable, and the identity function's derivative is the identity function, because the identity function is linear. So this identity prime at xy, that's just the identity on R n plus m. It's the identity linear map. So then, move this down. So then what we're getting is the ij entry of the identity matrix, right? The matrix representing identity in standard basis or whatever basis. You would get 1 if j equals I, and 0 if j is different from I. Okay, and if you still were not convinced that these are continuous functions, well, now you see that they're actually constant. They're definitely continuous. Okay, so we finished what we set out to achieve in this video, but we got a little bit more. So let's state that we finished what we set out to achieve. We got that f is a C1 function. So since this, which will be this kind of map, E to R, is continuous for all, it exists and is continuous for all ij. Theorem 9.21 tells us that f is a C1 function. C1 function on E with output in Rn plus m. And we can also use theorem 9.17 to describe the components of capital F, of the derivative of capital F, when we write it as a matrix using standard basis. So also for xy in Rn plus in E, we have we have that the derivative of f at xy is represented in the standard basis by, well, by something that takes forever to write down. So let me go ahead and write it down off screen. Okay, that took a while to write down. So this is using Theorem 9.17 again. So this is by Theorem 9.17, which is telling us what, when you have a differentiable function, what are the components of a standard basis matrix representation of the derivative. And they are this. So the first row is the partial derivatives of the first component of f sub 1. And then the second row is the partial derivatives of the second component of f sub 2, and so on, all the way up to partial derivatives of the nth component of f. And then n plus first, n plus second, and so on, all the way up to the last row, which is partial derivatives of the n plus mth component of f. And for each row, I've also split it into two portions. So in the first row, where you're looking at the partial derivatives of the first component of f, you've got partial derivatives with respect to the first variable, and then all the way up to the nth variable. And then n plus first variable all the way up to n plus mth variable. Now, filling in what these various components of capital F are, so what we found earlier is that f sub I, the ith component of capital F, is either little f sub I or is pi sub I. And it's little f sub I when I is 1 through n, and it's pi sub I when I is n plus 1 through n plus m. So that means, looking down here, all of the capital F sub i's, capital F sub 1 up through capital F sub n here, are actually little f. So there, I've filled in what they are, and I think for this next portion, I should take this part and move it down one and fill in an additional row. So let me do that. Like that, just so I can show how the pattern changes abruptly when we look at the n plus first row. So all of the capital F's here and down, from this row downward, are actually just pi sub whatevers. So let me make the replacements. Okay, there we are. So for example, d1 capital F sub n plus 1 xy, that capital F sub n plus 1 was actually just pi sub n plus 1, and so on for all of these. And we have discussed what we think is the derivative, the partial derivatives of the components of, we have discussed what we think are the partial derivatives of the projection maps, pi sub whatever. Because the different projection maps are actually just the different components of the identity map, the partial derivatives of these guys ended up being the entries of an identity matrix. So 1 if j equals I, 0 if j is not equal to I. So basically, going down a diagonal in this matrix as a whole, like here, you get a 1, and then all along the diagonal you get 1s, and everywhere else you get 0s. So all of the entries that have a little bit of blue in them are actually going to look like part of an identity matrix. Just like this. And another way I like to express this idea sometimes is just to say, over here we have a giant 0, a bunch of zeros, and over here we have what looks like part of an identity matrix. So, over here you have an actual identity matrix of size m by m. Okay, great. So we have proven that capital F is C1, and next we're interested in arguing that the derivative of capital F at x naught y naught is invertible. And now we have a nice way of looking at and thinking about the derivative of capital F at x naught, at any xy. It looks like this. Remember our assumption very early on was about, where'd it go? Was about the derivative of little f, and then take the first component sort of that. Down here in this matrix, you can see the derivative of little f showing up. It's all of this top half of the matrix. And when we say subscript x, take the first part, we're kind of taking this block here. So this picture really, I think, can help, is really something you should keep in mind and helps understand how the derivatives of different things are related.